We learned in the last lecture how to do a noise analysis and calculate out the total noise from various contributions around the circuit. We landed up with an amplifier with a noise of about 18.5 nanovolts per root hertz, which was quite a large figure. And this time we're going to look at what can we do to improve this design. Can we make a better design that will perform with a better noise performance than using the TL071. Looking at the results from this calculation, it's clear that the noise is being dominated by the input noise voltage of the amplifier. And if we calculate out the noise figure, we land up with a total noise equivalent at the input of 18.5 nanovolts. Our noise from the source resistance is only 1.82 nanovolts, so that gives us a noise figure of about 20 dB, which is a very poor noise figure performance indeed. Let's look at what's contributing to that. And if we go back to the equation on the previous slide, we discover that the amplifier contribution is 18 nanovolts per root hertz. The feedback network is contributing 3.86 nanovolts per root hertz, and the source resistance is only contributing 1.82 nanovolts per root hertz. These are the orders in which we must try to attack the noise problem. The biggest one is clearly the 18 nanovolts per root hertz for the amplifier, so we have to improve that. Feedback network, it's a little high, so we should try to look at that. And the noise from the thermal noise from the source, we are fixed with that because we cannot change the source. And the current noise into that thermal source impedance of 200 ohms is very small, so we can ignore that. Given the restrictions, all we can do with the amplifier, because it's part of the datasheet, is we need to choose another amplifier. And to look at the feedback network noise performance, we will look at reducing the effect and impact of the feedback network on the overall noise performance. Noise current, because it's only flowing into a 200 ohm resistance, a very low impedance, we can probably ignore that, but we'll still do the calculation nevertheless. Now let's do the analysis and find out what the numbers look like in improving this noise design overall. First of all, if we go back to our list of amplifiers, which I've given out in several lectures before, the lowest noise amplifier that you have been given is an LT1028C, manufactured by Linear Technology, and it has a noise voltage of 0.85 nanovolts per root hertz, which is incredibly good, but it does have quite a high noise current of 1000 femtoamps or 1 picoamp per root hertz. Let's look at how this amplifier will perform in our circuit. Presently, we have the amplifier configured with a gain of ×10 using a 9K resistor and a 1K resistor. Let's see what happens if we change the resistor values to lower values. Does that also improve our noise performance? So here's our revised design. We have our source of 200 ohms, as we always had, but in this case here, although we've kept the gain still at ×10 as a non-inverting amplifier, we've reduced the value from 9000 ohms down to 900 ohms and 1000 ohms down to 100. This has the effect of meaning that we only have a 90 ohm power resistance here. And now we've changed the amplifier. Let's run through the analysis again. Exactly the same as we did with the TL071, but this time we will use the parameters for the LT1028C. From our feedback resistor, because we've now gone from 900 ohms down to 90 ohms, we have reduced the noise contribution from the feedback resistor from about 3.86 nanovolts per root hertz down to about 1.2 nanovolts per root hertz. Similarly, we've also reduced the contribution from the noise current flowing into the 90 ohm resistor because it's a much lower impedance, so we've effectively improved it overall. So we only have a contribution of about 0.09 nanovolts per root hertz, which gives us a total value here of 1.22 nanovolts per root hertz. The reason that this parameter here disappears is that when you square it, it goes so small it doesn't materially affect the calculations. Going through the same steps before, we can now add in the noise attributed from the feedback resistors and the current flowing into the inverting amplifier node and as a 1.22 nanovolt per root hertz voltage source here, which is in series with the amplifier noise of 0.85 nanovolts per root hertz and the Thevenin noise source from the 200 ohms. And we still have to deal with our noise current flowing into the 200 ohm source impedance. Calculating out the figures here, we get 1.22 all squared plus 0.85 nanovolts all squared, which gives us approximately a 1.5 nanovolt per root hertz equivalent noise source for Vn. And if we work out our Thevenin voltage, we know that's 1.82 nanovolts per root hertz. And calculating out the total noise source, which is the Thevenin voltage, plus the Vn, plus the noise current into the source resistance, we land up with a total noise performance of about 2.36 nanovolts per root hertz noise referred to the input. Now if we calculate out our noise performance, we discover we have a noise figure of 2.25 decibels, which is much better than the previous example, which was 20 decibels. By changing the amplifier and by changing the feedback resistors, we've made approximately a 17.8 decibel improvement. And if that was a radio antenna, perhaps a radio dish, you've actually improved the size of the radio antenna by making it 8 times smaller because of the improvement purely from better noise design of the amplifier. The problem set out to say what is our total noise across a 20 kilohertz bandwidth. So if we take the square root of 20 kilohertz, which is approximately 141, then we work out that our noise spectral density of 2.36 nanovolts per root hertz corresponds to a broadband noise of about 0.33 microvolts RMS appearing as an input referred noise to the amplifier.